Hi everyone, my name is Alan Morales, and in this presentation, I'm going to talk about random forests and how we use them in a prescriptive analytics project. First, I'll use a heart disease example to explain the technique, and then I'll move on to our own logistic dataset and show my results. Okay, so what is a random forest? A random forest is a machine learning algorithm using two classification and regression instead of training just one decision tree. It builds many different trees on random subjects of the data and a random subjects of the variables. Then it combines all the predictions, usually by measuring both. This enables approach reducing overfitting and usually give better accuracy than a single tree. Um, to introduce the method, I'll start to public heart disease dataset from Kaggle. Each row is a pattern, and the target variable tells us if the pattern has heart disease or not. We have clinical features like age, cholesterol, blood pressure, maximum heart rate, and ST slope. This is a very classic binary classification predict if the patent is a risk on heart disease and zero otherwise. Here are the QR code of the dataset that I use and the QR of the example of the explanation that I follow to do it. So here you can see some of the main variables used in the method model. For example, chest pain type, resting BP type, cholesterol max HR, existing angina, and ST slope. These clinical measurements are the inputs that the decision tree will use to separate patterns into disease or no disease. First, we load the package in Python and read the Excel file. Then we separate the dataset into feature X and the target Y, which is the heart disease label. This is a standing pre-processing step before training any model. Next, we split the data into training and test sets using train test split. Then we create a random forest classifier with 200 trees and a fixed random state for reproducibility, and we feed it on a training data. Finally, we use the trained model to make predictions on the test set. Even though a random forest uses many trees, it's useful to visualize just one of them to understand the logic. Here you can see one decision tree from the forest applied to the heart disease data. Each node represents a question of the variable. Each path from root to leaf are rules of the classify patterns into a risk or no risk. At the top of the tree, the st-slope flat variable is used to make the first split, meaning it is very important for separating patterns. As we go down, we see conditions on exercise angina, chest pain, all peak and resting BP. Some labs are almost pure, for example, the purple leaf that predicts heart disease with a very high proportion of the positive cases. This visualization helps us to translate the model into simple if-then medical rules. To improve performance, we don't just keep the default random forest. We define a search space for several hyperparameters, the number of trees, the maximum depth, the minimum samples to split and to be a leaf. Then we use randomized search CV with cross-validation to automatically explore many combinations and select best on based on accuracy. Here You can see the output of the hyperparameter search. The algorithm found that the best model has a specific depth, number of estimators, and minimum samples per split and leaf. With these settings, we obtain a cross-validation accuracy close to 0.86 and similar test accuracy with the best model, which confirms that the model generalized well. This confusion matrix shows how the predictions are distributed. The diagonal cells represent correct classifications, while the off-diagonal cells are errors. We can see that most patterns are correctly classified and the number of false positives and false negatives is relatively low. Numerically, the model reached around 88% of accuracy with precision little above of 0.90 and recall around 0.89. So overall, the random forest is quite strong in detecting patterns with heart disease while keeping the number of false alarms under control. Finally, this bar chart shows the feature importance scores. The most influential variables are ST-slope, O-peak, exer- exercise-induced angina, and cholesterol. This confirms what we saw in the three visualizations. The forest consistently relies on a subset of key clinical variables to make it a decision. Now, I move on for medical example to our dynamic supply chain logistics team project. One important lesson from the heart disease trees was something we can get perfect node with entropy equal to zero, but that node may contains only three samples. So even if it looks perfect, it's not representative of overall population. So that experience motivated us to design a more robust model for our logistic data using random forests to look for patterns that are stable and generalizable, not just based on few or observations. Our logistic dataset comes from Real Network in Southern California between 2021 and 2024. It includes detailed information about vehicle behavior, road conditions, delays, risk scores, and operational constraints. Our main goal is to predict the risk of level of each delivery, low, medium, and high. The motivation is very practical. Companies want to reduce delays, optimize operations, and anticipate risky routes before problems happen. Here, you can see a subset of the variables that we use. We have delivery time, delay probability, road and traffic congestions, etc. In total, the dataset contains more than 32,000 records and 26 variables, which make it rich enough for clustering and trees based on models. The problem we address is that companies generate huge amount of operational data, but they don't know how to translate into insights. It's not obvious which routes are more vulnerable to delays, how external factors impact deliveries, or where the main operational risks are concentrated. In this project, we use clustering, decision trees, and random forests to uncover patterns, classify the routes risk, and support better logistic decision making. Before building predictive models, we explore the data structure with k-means clustering. This PCA plot projects the 26 variables into two principal components and show four clusters around 32,000 logistic dimensions. PCA reduces dimensionally so we can see the cluster structure and how the routes group together in terms of behavior. In this second PCA, we view the two things. First, because PCA compress all variables into two components, some overlap between cluster is normal. Second, even with the overlap, the four clusters are still clear, distinguished, which means our segmentation is real operational different between type of routes. Here, the red stars indicate the cluster centroids. Each centroid represents the average behavior of one of the routes. For more congestion risks or higher risks of operation. Just as in heart disease example, each split corresponds to a question about variables and leaves classify the route into low or for these trees we see that traffic congestion is a differential variable. It appears at the top of the tree and drives the main split. Routes with low congestion classify as safer, while routes with high congestion require evaluation. Other variables such ETA, estimated time arrival, variation, and operational delays. Looking more closer, we find two clear patterns. First, high congestion routes combined with large delivery time and risk lives with many samples. That means that patterns is stable and not just outliner. Second, routes with low congestion stable ATAs and mild external usually land in low risk, reflecting smooth and predictable performance. The third that we can see is the operational delays, for example, longer customer clearance or longer loading time. Here we switch from a single tree to random forest training on the logistic data. This slide shows tree 1 and tree 2 with maximum depth of 3, even though each tree is training of different random samples. The tree 1 highlights that low shipping costs together with good cargo condition usually lead to low risk. The tree 2 shows that low historical demand increases variability and often pushes routes into moderate risk and high risk. The, the 3 confirms the same story. Again, we see shipping costs and cargo condition near to the top with congestion driving many on high risk leaves. Putting three trees together, we can summarize the patterns across all of them are small sets of features, appears shipping cost, historical demand, cargo condition, and congestion level. Bad cargo condition or high congestion almost always lead to high risk classification, and factors like good cargo condition, fast customer, and low delays lead to low risk. When we compare the single decision tree with the random forest, the tree gives us an initial, very interpretable view of how routes are classified into low, middle, and high risk. And however, the random forest goes a step further by telling us which of those factors remain important across many different trees. The random foster forest also reveals interaction that were not fully visible in the single trees. Overall, compared to a single tree, the random forests provide more robust and less noisy rules and help us to identify patterns that hold across the entire dataset. To summarize the comparison, the decision tree is simple and high interpretable. It shows how risk is assigned step by step to noise and to the particular train test split. Overall, we can say decision tree help us to understand how decisions are made in very transparent way, while forests help us to understand which factors truly matter in a consistent way across the dataset. Combining both views, managing strong predictive to support logistic planning in a risk management. Thank you so much for your attention.